Okay, so we saw here that this algorithm, if you know A, B, and C, is pretty easy to follow. So this just says there's a register over here, and you calculate B times -1 to the A, and you put it in that register, and whatever else was in that register is no longer there. And you calculate C times B, and you put that in the C register. Now when you use B, you use what's in the B register, which is the value you got up here, right? The previous value is wiped out. It's gone. It's nowhere to be found unless you put it into a different register. Like you could let that go into, you could let the value B go into the register Q and use it later, but you have to have a register for it. So just base here, this goes into this register, 2 to the A goes into the A register. And when you calculate this, of course, you're using the existing value of A, but then you replace A, okay? And 2 times B goes into the B register. So if A, B, and C are 4, 5, and 6, you have, this one gives you 5 here times -1 raised to the 4th power. The strategy here is you would expect people to have even and odd numbers in their first name with relatively 50-50 chance. So you'd have a 50-50 chance here that B would become negative. Now you still replace B with 5. Just because B is already 5, you still go through the process of putting that into the register. You remove the one that's in there, you put the 5 in. And of course it turns out to be exactly the same, but if A was an odd number, you'd have gotten -5, and that would have gone into the B register. And then you just do the same thing step by step. And then I say, okay, here's a problem. Test the following. A plus B equals C. The backward apostrophes mean this is a variable with the value of A, right? And then you do that, and for these values of A, B, and C, it's clearly not so. But it's possible that I would have set up some mysterious sequence of calculations here, of steps, that would make A and B equal to C, or maybe with a 50-50 chance. Okay? So, and then I'll state a problem, and it probably wouldn't be that one. Although, just to test whether you know how to do this on homework, I might ask you to do something like this. Okay? So, that's one thing. Another is slope versus midpoint. People getting this backwards. I've seen that on a number of papers where you do midpoint versus slope. Slope versus midpoint, and where did I state it? Anyhow, slope versus midpoint is this. The midpoint goes first, that's the independent variable, and you graph dependent versus independent. And that's a convention that's pretty universal. And when you graph something versus something else, the first something goes here, the second goes here. So if you're doing slope versus midpoint, it looks like this. That goes with this table, and that goes with slope versus midpoint. So be sure you do that, otherwise your graph ends up on the side and doesn't make any sense. Doesn't look right. Okay? Okay, unit circles. I'm not sure everybody's got this unit circle thing down, but this is a circle of radius 1. I'm not going to write that here. We understand this. And the distance from here all the way around is 2 pi. The clock positions, and we go in this order, so we don't go from 1, 2, 3, 4, 5, 6 like a clock does. We go counterclockwise starting here, starting with the positive x-axis, and we measure how far we go. If the distance around here is 2 pi, then 1/12 of that, because there are 12 hours in the clock, is pi over 6. 2 pi divided by 12 is pi divided by 6. So that point is an arc distance pi over 6 from 0. Now I've seen at least a couple of things where somebody will put another pi over 6 here. So they write pi over 6 here, pi over 6 here, pi over 6 here. Well, that is how far these things are apart, but that's not what we're using to measure angle. We're associating the angle with the arc distance starting here and going all the way to this point. So that from here to this point, that's 1, 2, 3, 4 pi over 6s. That's 4 pi over 6. I don't want to confuse the issue by reducing that to 2 pi over 3, but normally you would do that. But just crudely, you could multiply pi over 6 up through 12 pi over 6, which would be back here. And then when you do your table of the x and y coordinates, which are clearly not 0.9, 0.5, 0.5, 0.9, etc., and you plot the x coordinate versus the arc distance around to that point, or the angle in radians, which is what that is, you're going to get a graph that looks like this one. Okay?
Using what?
If you plot the x coordinate versus this distance, you're going to get this graph, which many of you recognize as a graph of the cosine function. And that's how we define the cosine. If we do the y coordinate versus, this number, so we do 0.5 versus pi over 6, right? 0.9 versus 2 pi over 6. You would get a graph that looks like this. That's your basic sine function. And we've defined those so you can easily find that in the notes in the videos.
Which one is sine?
Again?
I was writing this down. Which one is the sine function? You just said.
Number one, make sure you know where to look it up, because I won't be here to answer, past today. Of course, I can, answer questions on the bus and stuff. This is the sine, this is the cosine. The y versus the arc position is your sine. The x versus your arc position is a cosine. And we defined that day before yesterday, I think. Maybe even the day before that. So you can look back and see. Okay? Now, another thing is, if I do a slope graph for this graph, that means like I do a trapezoidal approximation graph and graph slope versus midpoint. Slopes start out negative. They start out at 0, but then they reach a maximum negative value here, and then they go back down to where the slope reaches 0, right? Well, that would be like this. Slopes start at 0, go to a maximum here, a maximum steepness, and back to 0 here. And then the slopes start going positive, and they get real steep, and then they go back to 0, and it's like this. So that the slope graph for your cosine graph is this, which is the negative of the sine graph. Now, it won't exactly be, because you're doing a slope graph of a trapezoidal approximation. The smaller the intervals you use in your trapezoidal approximation, the more closely this would match the negative of this one. Okay? And then if you do a slope graph of this one, it's going to look like this, which is the opposite. You flip the cosine graph over and you get this, right? And that's just your first and second derivatives of the cosine, but you don't need to know that. That's something you learn in calculus. But if you understand how these graphs are constructed, and you get a calculus class that actually asks you to think about things, okay, this is going to be helpful to visualizing what's going on and understanding all the symbols, because that's always kind of a thing you gotta overcome. Okay, the symbol thing is kind of a jump. Okay, and then same thing, your sine slope graph is this. That's just the cosine graph. So the slope graph of this one is basically just this one. Okay, and the slope graph of this is this one, but turned upside, reflected around the horizontal axis, okay? So it'd be the negative of the sine. So right there's a rule for the derivative of the sine and cosine, but we don't have to worry about that. I'm not trying to teach you calculus, I'm trying to teach you how to look at graphs and interpret them when you have trouble with interpretations. We're going to talk about that. Gave you an algorithm basically for interpretation yesterday morning, okay? Ask yourself what the rise means, ask yourself what the run means. Of course, you got to know how to take a picture of the difference quotient, and then you have to know what to do with it. It's pretty straightforward, so we'll do some of that. Okay. Also, right here is your graph of the sine, and here's your graph of the cosine. You've made those graphs. You know what they are. Yeah, make sure you know how to identify them. Okay, another thing is some of you are doing getting errors when you're trying to graph the normal curve, okay? And the expression you see for the formula is this, okay? And you're getting the order of operations wrong. And that's not too surprising. I'm getting to the point where I just have to start my pre-calculus classes with an exercise in order of operations, and that clears it up. After that 5-problem exercise, and nobody has a problem with it again. Distant students, even distant students who end up not doing very well, would get it. So I need to start doing that, and I should probably have done that with this group, but you guys will understand it quickly. Okay. What's the first symbol that tells you an operation that needs, what's the first operation that needs to be done here? This. You know you do exponents before anything. Well, unless they're parentheses. Now I could have used parentheses here, but that can confuse things if you got too many parentheses. It can get hard to read. Besides, it's totally unnecessary if you understand the order of operations, which even not very well prepared pre-calculus students were able to do in my distance courses for 20 years. Okay? So, you apply the power 2 to what? What is it you take the second power? This means take the second power, right? What is it you raise to the second power?
Negative z.
No.
Z.
What's the thing immediately to the left of this? Z. There are no parentheses around the negative z. The negative sign is just there. It's not z. And it's only z that gets squared. So if you think you're squaring negative z, well, I think even by the time I graduated high school, I knew that, but I could be careless with it. Okay? I had a pretty good high school background. And I learned the stuff pretty well. So I had to get used to that, not make that mistake, okay? So get used to it now, because otherwise it'll bite you sometime when you really don't want it to. Like maybe on the final for this course, a bit later on. Okay? At any point from now on, that can bite, okay? So you're squaring z, not negative z. If you wanted to square negative z, there'd be parentheses around it. You square exactly what precedes this. The negative sign is a multiplication by -1, essentially. And that doesn't get done before the square. Now, what's the next thing you would do? You have two choices. Because you do multiplications and divisions in any order, right? So you could apply the negative, whatever you get when you square z, you could then make it negative. Okay? But if you square negative z, you're always going to get a positive, and you're going to get a bad result. Okay? So you'd have a negative number here that you divide by 2, and now e is raised to that power, right? So this means raise z to the power 2, take the negative, and divide by 2. Make sense? Okay, so those are little things that I wanted to clear up, because those are fairly common examples of things that you tend to do wrong. Another is you make your graphs too small so everything looks linear. And you don't check to see if it's linear, and you just draw a straight line through it without calculating slopes. Okay? You know, you look at the numbers and pretty well see whether it's linear or not, and see whether this one's steeper than this one, right? So when I ask you to graph 3 points for, let's say, sane-demented populations, and you draw 3 points that are in a straight line, it ain't so. And you didn't check it, okay? It's easy to check because, well, it's easy to check. So make sure you kind of do that. Make your graphs bigger. Not everybody needs to do that. Some people make just beautiful graphs, and some people are making really sloppy graphs that are big and still show what they should show. So it's okay. But if you're making a tiny graph, even if it's meticulous, if it's too tiny, you're not going to be able to see the behavior, okay? Another thing, it's a little late to do this, but you do have homework due Monday. Don't just leave it blank, a problem that you don't know how to do. At least jot a note, okay, this relates to water flowing through a tube. that means there was some mental activity other than, what the heck do I do with that? Okay? And it also kind of tells me what it is you don't know, because I don't remember which problem has which number. I mean, I kind of do, but I don't always. So right there, I'm losing information, and I'm not going to go look it up. Okay, partly because my Chromebook just all of a sudden started not accessing VHCC's network, which has an antenna right there. Okay, and I think it's probably the Chromebook. I don't think it's VHCC's network. Something weird happened. And I didn't have time to troubleshoot it because I was busy doing other stuff. So normally I have the Chromebook there and I can flip over and find stuff. Now, and none of my other computers are allowed to be on the internet because of virus problems. So, so as a result, when I look at your homework, I can usually figure out what's what. But when not everybody leaves a problem blank, I might not know what problem that was, so I might not have important information. So for that reason, you should at least do that. But even more importantly, if you make that note, you at least have the mental activity to make that note, okay? And at that point, you've actually done something where you think you have or not. Also, it prompts you to say, okay, maybe I ought to look at this. Maybe I ought to look at that video. Not hard to find. Okay, it takes time, and you know, when you're under time pressure, especially in the middle of the week, it's hard to do that. I understand. Anyhow, yeah.
None of us did this problem last night on the homework. Do you think we could go over it? I have the problem with me right here.
That's
We,
what I
we,
mean.
we can get to that. Let's just wrap this up. Okay. So there are a couple other comments I have, but let's go ahead and look at problems.